the first thing that I want to say is that I'm extremely glad to be here with you to discuss not only about neuroed, but about brain ischemia. Brain ischemia, as you know better than me, has experienced many possible drugs, many developments. You have been involved in many clinical trials, and up till now they have all failed. Of course, we are left with TPA, but TPA is important, but it's important for a small part, relatively small part, or anyway, insufficient part of the patients. And of course, when the clinical trials have taken place, you can analyze the clinical trial, try to understand why they didn't work. Of course, they might not work because of the clinical trials. They might not work because the science before was done on animal models, and of course, animal models are never like the humans, because when we work with rats or with mice, they are all young, they are all in the same strain, they are all males, they never had disease before, so it's a completely different matter. But I think the main reason why, and I think, and many other people think, that the main reason why these clinical assays failed is here. Up till now, people have looked for the magic bullet, for the magic target, the magic molecule for the magic target. And you've all experienced that. You have experienced that for glutamate receptors. There have been a lot of drugs developed for glutamate receptors. You have experienced that with calcium channel blockers, with sodium channel blockers, with things that eliminate free radicals, etc., etc. And of course, many of these experiments were done with the idea that the key word was neuroprotection. And the idea is that the first question that comes to mind is that you make the neuroprotection in the very early phase. Can you have a neuroprotection without a reperfusion, number one? And the second thing that comes more and more evident is the window time of administration. Of course, in ischemia, there is a lot of glutamate release, and it's toxic. And you want to block this toxicity, and then you block the glutamate receptors. Okay, if you do that early, that will neuroprotect. But this is forgetting that actually in later stages, when repairs take place, where synaptogenesis takes place, glutamate is needed for that. So first stage positive, second stage negative. It's the same for calcium channel blockers. You prevent the invasion of calcium, but later on you will need calcium to trigger the reparation system at the DNA level. You have tried molecules that will inhibit proteases, the matrix metalloproteases. Of course, it's easily understandable that if you block the matrix metalloproteases in the first stage, you will prevent some destruction. But in the late stage, when repairs come, if you inhibit the matrix metalloproteases, then you will not favor the neuroblast migration for repair, and etc., and etc. So this problem of window time of drug administration has been a key problem. And of course, in classical development of medication, you have these things that is unavoidable. You have a good idea. You have your magic bullet for what you think is your magic target, and you go from the bench to the bedside. And whether we like it or not, up till now, unfortunately, it has not worked. It has not worked for most patients. Maybe we've missed something, but it has not worked for most patients. So the idea is actually to look for something else in front of a lack of medicinal treatment. And what we are going to discuss today, myself and then Chris, is a bedside to bench approach, the reverse approach. we're discussing about a mixture of extracts of plants that has been given to a lot of people in China and in Asia. So it's there in China, in Asia. And these people believe that it works since they prescribe it. And we're going to try to find whether there is a scientific rationale to it. So it's the reverse strand. And the idea is that this may work because instead of having the magic bullet for the magic target, it's a search for what may be a combination therapy, because in these different plants that have accumulated in the maturation of this traditional medicine, there are probably a lot of molecules doing, as you will see, a lot of things. And the different things is that most of the drugs that have been developed up till now are drugs which were aiming towards neuroprotection. And what traditional Chinese medicine tells us is that this drug, this particular drug, is given late to the patient. It's given in China. And Chris will come back to that, I am sure. It's given weeks or months after people have had a stroke. And this by itself will suggest that the treatment has some kind of action to stimulate the brain's own restorative therapy. So it's where we started. And the compound, as you know, is Neurored. So what is Neurored? Neurored, there are two versions of Neurored. So this version that Chris will discuss a lot, which is a version with 40 components. And it has plant components and other type of components. And this is the Chinese medicine. And this is the other version, the version that is here and that is everywhere else in the world, that contains the 9 different herbal components, the 9 different extracts. And to cut a long story short, at the scientific level, at the discovery level, the two compounds behave essentially identically. So, repair. When it comes to repair, when it comes to neurogenesis, for those who have forgotten a little, you start with the neuronal stem cells, you make neuronal precursors, and you go to mature neurons. And that is taken in a number of steps. And for each step, we scientists have a number of markers. So we believe that we can follow these steps adequately. So from now on, we don't try to do imaginative science. And this is what we don't try to do that at all here. What we want to do is that there is something that is said to be beneficial in patients, and with very classical ways, we want to see whether there are compounds which do something that we can describe at the cellular and at the molecular level, to give a scientific substance to what was observed in the traditional Chinese medicine. So the other thing that has come in, so for a long time, people have thought that there was no neurogenesis in adult animals, and but actually, since I think 1998, the situation has changed. We know that there is neurogenesis, and not only we know that neurogenesis, but through the work of a lot of people, we know that this neurogenesis in the brain is increased after the brain has had some kind of trauma, be it epilepsy, be it ischemia, be it trauma. So in all these cases, the brain reacts in having more neurogenesis to try to repair. So actually it's a fight between the trauma that tends to kill cells and the neurogenesis that tends to repair, but the repair is never enough. So you see here that the neurogenesis takes place, as many of you know, in spatial zone, the subventricular zone, the subgranular zone of the dentate gyrus, and then the neurogenesis can go around to repair places where there is something to repair. So what about neurored? We know very little of the basic science in humans, of course, because extracting neuronal cells from humans is not easy. But at least, and I start with this experiment, at least when we apply neurored on human stem cells, so these are human stem cell-derived progenitors, so the progenitors look like that, you know, they assemble in structures that are called rosettes, and these rosettes mature, and from these rosettes you make the neuron, you make the glial cell, you make the oligodendrocyte. The first thing that we see is that the rosette shape is not changed when we add the compound. The second thing we see is that when you add the compound, the number of rosettes, as you see in this particular experiment, increases by a factor of 4. So yes, at least at the scientific level, you increase the number of the progenitor neuronal cells. Now, what about neuroblasts, the second step? So here we go back to mice or rats. In this case, it's mice. So we take the cortical cells of mice at a time where they divide. We put them in culture. And if you put them in culture for 14 days, as you see, if there is no treatment, the network disappears after 40 days. If there is a treatment with the extract of neurored, you see that between the first day and between the 14th days, in the 14th days, cells are very much healthy, and at 14 days, if you compare this and this, there is a lot of difference. So here, what we use is a marker that is a traditional marker, which is called double cortin, which is an important marker for neuroblasts, but which also an important molecule for the neuroblast to help it transit through the dangerous zones. And there are many dangerous zones in the transit of neuroblasts to repair after an ischemia. So you see that the compound, which is the one that Chris will discuss, the compound which is the original compound, and the compound with only the plant extract, they all behave the same and they increase this marker. So after that, it's automatic. Can you have a marker which underlines the growth of axons, the growth of dendrites? Yes, there are a number of markers, and there is a classical one which is called the growth-associated protein 43. And again, we analyze that in culture, and neurored will increase the expression of this growth-associated protein that is associated with dendrites and with axonal and with axon. So now you can also measure the neurite growth. So you can measure the number of neurites, or you can measure the length of the neurites. So you see that if you look at the number of neurites for different sizes of neurites, 50 microns, 100 micron, 150, the number of neurites increases. And also the length of the neurites, especially for the long neurites, will increase too. So it all seems to go in the right direction. So what about the formation of synapses, which is also absolutely important in the repair, in the plasticity in the brain? So here we take a classical marker, classical synaptic marker, which is called synaptogamins. They are key proteins in the neurotransmitter secretion. And again, you have here, the blue is the vehicle, and the other one, you have an increase of the expression of these synaptic markers. So an expression in the growth markers, an expression in the synaptic markers, an increase in the neuroblast. So now, of course, you need to know whether all that is only in culture or whether it's also true in the animal. So what we do here is that we give the animal the neurored. So at the very beginning, we didn't know how to give it to the animal. So we put it only in the drinking water. in the water they drink, and they liked it very much, actually. And we let them drink ad libitum for 6 weeks. You give you give Neurohead. Those who give Neurohead, they give it for 3 months. So they take it for 6 weeks, and then after that, we make an injection of a compound that tells us whether the neuroblasts form and actually go to mature neuron in the brain. So actually there are a number of markers. BRDU is something that goes only in the dividing cells. This is a marker of neuroblast. So, and as you see, we increase the neuroblast proportion in vivo this time. I mean, they drank the molecule, and then they increase the neuroblast proportion in vivo. Okay? So you have to think that a few thousands of cells each day are the one that at least in these animals, are the one which repair. So you increase the number of these cells, and you see that it also goes to the adult stage. Now, do you have any idea of the mechanism? We know very little of the mechanism, because the idea is that there are different plant extracts, and as I told you before, there are probably many, many molecules which do something beneficial for the animals and for the patient. But of course, when you think of repair, you think of growth factors. And one of the classical growth factors, which is extremely important for repair, is called brain-derived BDNF, brain-derived nerve growth factor. And the BDNF by itself increases after stroke, and it's extremely important for growth and differentiation of neuroblasts. But another thing which is important is that BDNF is also involved in the co-regulation of neurogenic and angiogenic responses. This has been shown by a number of people. So what does the compound do on BDNF? As you see, when you give the compound to the animal, and this is in the region, this is in dentate gyrus actually, there is a very significant increase of the BDNF level, of brain-derived neurograph factor group, and an increase of BDNF would mean for us an increase of the repair capacity. Now, what other type of mechanism do we have? We have another type of mechanism that we've discovered not such a very long time ago, which is close to my main scientific activity, which is an activity on ion channels. There are many ion channels. All the ion channels are important in the brain, of course, for bioelectricity, but there is an ion channel that is extremely important in the brain in relation with preconditioning. Preconditioning is you make a small ischemia. It will not harm the brain. Well, you know that in humans as well. And it will protect as a longer ischemia. In mice, it's 3 days later. It can protect completely. Or a small epilepsy, and a temporal epilepsy, and it will protect against ischemia. And how does that take place? And many, many years ago, we've shown that one of the important signals is a channel that is called the ATP-sensitive potassium channel. It's a potassium channel that opens when the ATP level inside of the cell decreases, and the ADP level, and of course in an ischemia, the ATP level decreases, the ADP level decreases, the ADP level increases, and the channel opens, and this, in preconditioning, this triggers a sequence which primes neuronal cells for more resistance and repair. That's preconditioning. Preconditioning involves this channel, among other things, for priming the neurons for more resistance and repair. And it turns out that in Neurohead, in this cocktail, you have an activator that also opens ATP-sensitive potassium channel. So actually, this activator is, for us, a mimic of the preconditioning, and will explain part of the activity. So the conclusion of this part is that pre- and post-treatment with NeuroRed have positive effects against stroke. I didn't discuss with you death, but it has effect on death. I didn't discuss with you functional deficit. It has an effect on functional deficit. NeuroRed activates ATP-sensitive potassium channel. NeuroRed stimulates neurogenesis. NeuroRed increases BDNF production. So now I'll come to something else that you don't deal with in your practice every day, but of course scientifically it's extremely important, and the other thing is that there is no medicine for that either. This is something for the cardiologist. This is global ischemia. This mimics a cardiac arrest, and when there is a cardiac arrest, be it in man or be it in there is a part of the brain that disappears completely, as you very well know. This is the hippocampus, and of course the memory that goes with it. And of course, for most of these patients, you can do nothing. You can do nothing but eventually hypothermia. And hypothermia, as you know, this will not, I mean, you do hypothermia and you cross your fingers. And we were discussing about multi-target treatment. If there is a treatment which is a multi-target treatment, is hypothermia, because hypothermia will decrease metabolism and do a lot of other things for enzyme, for channels, for receptors, etc. So here too, you have nothing else than a multi-target treatment. Well, we'll try NeuroRed on that. And when we try NeuroRed on that, what do we see? The first thing that we see is survival. In this particular experiment, we do a global ischemia, and about 20% of the animals die. If they have been treated with NeuroRed, all the animals survive. It's a question of life and death. And the other thing is that we look in the hippocampus, and we look particularly in the region of the hippocampus which is involved in memory, which is the CA1 region of the hippocampus, and you see that the number of CA1 neurons decreases drastically if you don't treat. But if you treat half an hour, 1 hour, 2 hours later, you see that you have a complete preservation of the hippocampus, and it goes to 3 hours. So yes, the product here also has an effect on global ischemia in protecting the brain very much. So again, mechanisms. So we can go rapidly. One of the mechanisms that has always been in the center of any ischemic attempt, ischemic event, is the production of free radicals. Do we produce free radicals in ischemia? Yes, we increase free radicals in ischemia in hippocampus a lot. And what happens when we treat the animals 2 or 3 hours later with NeuroRed? It decreases considerably the production of oxidation of lipids. That is one part that leads to death. In ischemia, of course, the mitochondria suffers a lot. And because of this suffering of the mitochondria, there are a lot of systems that are started, particularly apoptosis. And you see that with a marker which is called BAX, the mitochondria suffering, and of course, you decrease that a lot if you treat with NeuroRed 2 or 3 hours later. And then you can look at apoptosis, and then you can look at what we scientists call DNA laddering, the destruction of the DNA. And the story is the same. So there is clearly a protection. And in global ischemia, when you arrest the rat, there is also the heart, there is also neurogenesis. As you see, we measure the neurogenesis. There is spontaneous neurogenesis. So you make a global ischemia, and then there is neurogenesis that is in blue. But if you treat the animal, the neurogenesis is in red. So it's increased, this neurogenesis. And it's at 7 days, and it's at 22 days. So the natural neurogenesis to repair the brain increases and decreases, and in the presence of NeuroRed, it's maintained. Okay? And BDNF, of course, also increases, and increases more after a treatment of NeuroRed than without treatment of NeuroRed. So this is convincing, but of course we are interested also by behavioral studies. There have been a number of behavioral studies for focal ischemia. This is for global ischemia. So as I told you before, when you make a global ischemia, you lose your CA1 in hippocampus and you lose memory. So this is a very classical test, which is called the Morris-Water maze. So for those who do not know, this is a pool in which there is a platform, and you put the animal here, and the platform is situated in a milky water. So the animal doesn't really see the platform, but the animal doesn't like water and wants to go to the platform. And then if you train the animal for 4 days, the animal tends to go to the platform fairly directly after you've trained it. If your animal has undergone global ischemia and lost the hippocampus, then you see the animal is wandering around to find the platform and might not even find it. But if you've treated the animals with Neuroed 2 or 3 hours later, yeah, you see that the animals maybe not completely equivalent, but is nearly equivalent to the control animal. So, and the motor aspect, there are also effects on the motor aspect. This is one of the way to look at the motor aspects. So you put animals on a grid and you measure the grip strength, and you make a global ischemia. So this pre-surgery, you make a global ischemia. The grip strength decreases a lot, but for the animals which are treated, the grip strength decreases much less. You know, and what you see in blue is that this is for rehabilitation, and you know that extremely well. The grip strength will come back slowly, day 3, day 10, day 15. This is in blue. But for the animals which have been treated, the grip strength comes back completely at day 10 compared to that, and then remains. So the conclusion is that Neuroed has a potent effect in global ischemia. It protects against apoptosis. It protects against free radicals, in addition to what I said before. It protects mitochondrial function. What I didn't show you is that it activates kinase pathways, but this is very specialized, essential for survival and repair. It activates neurogenesis and BDNF production. So this is the list of the people who have worked with me, particularly Catherine Hurtaud on these things, and Brigitte Ottoniante for the human cells. And maybe I'll come back to the conclusion to tell you that when we started with that, I mean, quite frankly, we didn't believe we wouldn't find any ground science for explanation of this Chinese medicine. Fortunately, the first experiment was a good one, because of the people who work with me and not because of me, because I wanted them to try on hippocampus first, and they did it on cortical cells that are neuroblasts instead, and they did well, because that started the whole thing. And in animals and in cells, it works. Thank you very much for your attention.